Welcome, everyone, and thank you for being here for CCST's Expert Briefing. My name is Sarah Brady. I'm the Deputy Director of the California Council on Science and Technology. I'd like to open our briefing today by acknowledging that I am presenting to you from the tribal land of the Nisenan people. Sacramento has long been a gathering place for many local tribes. We acknowledge the Southern Maidu people to the north, the Valley and Plains Miwok peoples to the south of the American River, and we would also like to honor the Patwin Wintun peoples to the west of the Sacramento River. Today, I'll introduce CCST, our Disaster Resilience Initiative, and then welcome the moderator for this briefing, Gia Vacin. The California Council on Science and Technology, CCST, is a nonpartisan, nonprofit organization established over 30 years ago at the request of the legislature. CCST was created to provide science and technology advice from the wealth of outstanding academic and research institutions in our state directly to policymakers. California is lucky to have such an incredible network of expertise, and our job at CCST is to help amplify and translate the expertise in this network into actionable advice for policymakers. We do this through a number of mechanisms, including briefings like the one you are attending today. We host workshops, write peer-reviewed reports, and run the CCST Science Fellows program, where we place PhD scientists and engineers in the executive branch and the legislature for a year of government service and leadership training. As part of our mission, CCST is advancing work related to our Disaster Resilience Initiative to help the state better prepare for and respond to ongoing, complex, and intersecting disasters that affect public health, our economy, and our environment. These include climate change, extreme heat, which we're all experiencing today, power outages, and the COVID-19 pandemic, which are radically disrupting the ways in which Californians live and work. These disruptions, while often destructive and painful, can provide us opportunities to redesign our systems to be more resilient and sustainable. Through our Disaster Resilience Initiative, we seek to deliver science and technology advice to reduce harm and improve the lives of all Californians. Today, we are focusing on how hydrogen could help us decarbonize California's transportation sector, and in doing so, reduce what is currently the largest source of greenhouse gas emissions in the state. I would now like to introduce Gia Vacin, Deputy Director of Zero Emission Vehicle Market Development at the Governor's Office of Business and Economic Development. She focuses on accelerating the zero emission vehicle market in pursuit of California's goal of 100% ZEVs by 2035 for light duty and 2045 for heavy duty vehicles by coordinating state efforts, collaborating with public and private partners, tracking and expediting ZEV infrastructure in California, and identifying opportunities for additional business engagement and growth. Welcome, Gia.
Thank you, Sarah. Thanks for having me today. I just would make a couple of remarks before we get to meet our great panel today. So as many of you may know, the transportation sector comprises about 50% of California's greenhouse gas emissions and about 80% of the smog-forming pollutants. So California has aggressive goals to address climate change and pollution and really remains a leader in legislation and policy to help achieve these goals. Converting both light duty and heavy duty vehicles and medium duty to zero emission technology will be critical in getting to carbon neutrality while also eliminating the major sources of other harmful pollutants like particulate matter and nitrous oxides. And in California, we are investing in both zero emission vehicle technologies, so battery electric and hydrogen fuel cell electric. And today we're focusing in on hydrogen and what it can bring to our energy transition. So I have 4 experts here with me today that are working in different areas of hydrogen research. And so I'll invite each of them to introduce themselves and their expertise and share one specific challenge that they're working on today. And then we'll jump right into audience questions. Okay, so, and then I'll just say before we get started, if you have a question, please type it in the Q&A, and we'll do our best to get to as many questions as we can today. So first, I'd like to invite Dr. Jimmy Chen, the Managing Director of the Hydrogen Initiative at Stanford University.
Hi, Gia. You can hear me?
Yes.
All right, fantastic. As Gia mentioned, Jimmy Chen, I am the Managing Director here at Stanford Energy and a Managing Director of our Hydrogen Initiative that we kicked off in May of this year. It was a fantastic kickoff, and we've been building this community, this global community in hydrogen for the last 3 years. So to see it finally come to fruition was very exciting for us. I would also like to thank Gia and the CCS team for inviting me to be part of this panel. Just by way of a quick introduction, Stanford Energy is the community of researchers here at Stanford, the students, and also our global ecosystem of participants. And we are looking forward to enabling the global energy transformation. And we are also an anchor, a cornerstone of our new school of sustainability that literally just got launched last week after a tremendous amount of activity and stuff. So thank you again for inviting me, and I look forward to the discussion.
Great. Thank you, Jimmy. Next, please, Dr. Brian Ehrhart, who's a chemical engineer with Sandia National Laboratories. Hi, Brian.
Hi, Jib. Thank you. So my name is Brian Ehrhart. I'm a chemical engineer at Sandia National Laboratories, and I work primarily in the safety codes and standards space for hydrogen technologies. Sandia National Labs is a federally funded research and development center with main sites in Albuquerque, New Mexico, and Livermore, California. We have just a little bit under 2,000 staff members there in Livermore. The Sandia Hydrogen Program has been ongoing for a couple of decades now, focusing primarily on hydrogen behavior, materials, and safety, focusing on everything from hydrogen production, storage, and the safety codes and standards issues that surround hydrogen technologies. I myself am the program lead for the safety codes and standards sub-program here at Sandia. And so I tend to work primarily in that area, doing quantitative and qualitative risk assessments, as well as reviewing the existing regulations, codes, and standards for hydrogen systems. One particular challenge that we're working on now that is especially relevant to this discussion today is looking at some of the particular risks and what sort of best preventative and mitigative measures we could implement for high flow rate fueling of heavy duty transportation. And yeah, thanks. Happy to be here.
Great, thank you. All right, next we have Dr. Ahmet Kusoglu. Please, he's the staff scientist of the Energy Conversion Group at Berkeley Labs and the communications officer for the Million Mile Fuel Cell Truck Initiative. Welcome.
Thank you. My name is Ahmet Kusoglu. I'm a staff scientist in Lawrence Berkeley National Lab, working primarily on hydrogen and fuel cell technologies. I also serve as the communications officer for the Million Mile Fuel Cell Truck, which is a Department of Energy funded multi-lab consortium co-led by Berkeley Lab. In Berkeley Lab, which is located in Berkeley, California, we work on research and development of clean hydrogen production, use, and storage across multiple science areas and applied technologies to overcome barriers and realize hydrogen at scale and improve discovery to the deployment for immediate impact. So one of our focus areas with the Million Mile Fuel Cell Truck Consortium in the hydrogen space is to focus on decarbonizing heavy-duty transportation, and we aim to improve the durability and efficiency of hydrogen fuel cell technologies to enable their commercialization for heavy-duty vehicle applications with an initial focus on long-haul trucks. Thank you again for having me, and I look forward to the discussion.
Great, thank you, Ahmet. And our fourth panelist is Dr. Iryna Zenyuk. She's the Associate Director for the National Fuel Cell Research Center at UC Irvine. Hi.
Hi, thank you, Gia, for having me here. Yes, so I'm also associate professor in chemical and biomolecular engineering at UC Irvine. So National Fuel Cell Research Center is 24-year-old center, and our mission is to accelerate development and deployment of hydrogen technologies. So we work at scales from fundamentals all the way to deployment. And one challenge is, of course, for heavy duty trucks is how do we design fuel cell systems to be durable to make sure that the fuel cell trucks can drive that 1 million mile. Thank you.
Thank you. Yeah, great. So as you can see, we have some great expertise here crossing, a lot of the areas of the hydrogen and transportation space. So let's get right to it. A reminder, if you have a question, you can type it into the chat with your name and affiliation, please. And our first question comes from Chris Divin from the California Department of Housing and Community Development. I think this question will Jimmy, if you could take this question to start. Where does hydrogen come from, and or how is it made? And then why is it better than gas and diesel? Oh, you're on mute.
Thank you. Thank you for that question. Currently, the vast majority of hydrogen that's used in industry and other uses comes from fossil fuels, primarily from natural gas, through a process that's steam methane reforming. But basically, you convert a hydrocarbon, a molecule with both hydrogen and carbon in it, and you convert it over to extract the hydrogen out. Okay, that's the way that most of the hydrogen is made today. What's really exciting is the ability of taking and making hydrogen from water using electricity, especially if the electricity is renewable electricity. That's what makes it really exciting. So you can imagine a scenario where you have solar or wind, renewable electricity, and then you add water to that, and then you get out hydrogen and oxygen. And that makes it extremely exciting. On the other end of the spectrum, what's really exciting is if you were to convert this hydrogen and air or hydrogen and oxygen in a fuel cell, say in a vehicle, your output or your resultant is water. So now you're looking at a condition where your waste product is water as opposed to some sort of carbon dioxide or some sort of other gas. That's what makes it really exciting, especially when we're looking for solutions toward a renewable world. In addition, the other thing which I don't think many people realize is that if you look at the amount of energy converted into transportation miles, okay, through a fuel cell, it's actually much more efficient, up to 2x. As opposed to taking a gasoline, then you burn it, and then you look at the amount of miles of it. If you actually convert hydrogen into electricity and then power that vehicle, okay, the efficiency is much better, upwards of 2x. That's another thing that's very exciting. So I hope that answers your question. If you have any other questions, please, or other panel members have any other thoughts or additions to that. Thank you.
Thank you, Jimmy. Anybody else want to add? I have just one thing that I thought to add, actually, when we talk about a lot of the hydrogen today being produced from steam methane reformation, which does have a GHG emission, and so there has been I've heard concerns over the years of what does it mean when you're producing this fuel? But I'd like to point out that even gray hydrogen, as it's called, like produced from steam methane reformation, is still I think that the figures I've heard it's still 60% better than a fossil based fuel, and remember that we don't have any of the pollutants that come with it, so we're at zero pollution there. Great.
That's the coolest thing, quite frankly. When I was driving my MRI, I love the fact that the only output I had was water.
Yeah.
It's so cool.
Yeah, definitely. Great. All right. Our next question here is from Carrie Kisco, from the state of California Department of Conservation. The question is hydrogen safe for vehicles, and what happens in a crash? So Brian, I think this is a great question for you.
Yeah, so hydrogen is a flammable gas, and like any sort of flammable material, does need to be considered and treated carefully when it comes to its storage, transportation, and use, and the particular properties and behavior characteristics of hydrogen absolutely need to be taken into account. Hydrogen is non-toxic and won't do anything like leak into topsoil or groundwater or anything like that, but it is flammable. That is kind of the main hazard of hydrogen. It can disperse and tends to be very buoyant, so it does tend to disperse easily into the air and kind of go, up and away from a potential leak point. So it's really kind of those sort of near scale, right, kind of very close to the leak point locations that need to be considered when it comes to a hydrogen leak. The hydrogen is currently used in vehicles, including thousands of light duty vehicles around the state of California that are on the road today and are currently operating. In a crash scenario, that's of course a very, very important and critical consideration. These vehicles have a number of both federal and international standards that they have to meet, especially when it comes to crashworthiness. So both the DOT, NHTSA, Department of Transportation, US Department of Transportation has particular characteristics, as well as there's some United Nations global technical regulations that also apply to the hydrogen tanks that are on board the vehicle. These include everything from crash testing to fire testing to corrosion testing, and these vehicles, before they're put on the road, before the tanks are allowed on these vehicles, they need to be able to demonstrate passage and conformity to these pretty abusive and pretty stringent safety standards. And so a lot of work has gone into developing those standards, and a lot of the vehicles have to meet those standards before the hydrogen can go on the road today. Of course, figuring out, in kind of more worst case or severe crashes is still definitely a concern. We've done some research at Sandia looking at kind of the effects of crashes in tunnels, for example, and that work continues to be ongoing. But even these tanks really can put up with quite a bit of abuse. There's even been some like ballistics testing of like firing like high caliber like rounds into these tanks, and typically at even in the worst case, a hole is ripped in these tanks, the hydrogen escapes, potentially a fire in that kind of immediate vicinity, but that's typically the extent of the outcomes.
Great. Thanks, Brian. Does anyone else have something to add? Was pretty thorough. Thanks. Okay, great. All right. Our next question.
Actually, I'm sorry, Gia. I saw a comment in the chat, which is a great point. So the Center for Hydrogen Safety is actually a fantastic resource for all things related to hydrogen safety. And they also have some trainings about hydrogen in general, as well as some first responder specific trainings available through the Center for Hydrogen Safety that I think are especially relevant to any sort of hydrogen transportation applications, but particularly for those kind of crash scenarios. So yeah, that's a great point.
Right. And their h2tools.org is where you find that. So, but many resources there. That's in the chat as well. Excellent. And thanks, Juan, from the Hydrogen Fuel Cell Partnership. Thanks for that great addition. All right. Our next question is from Larry B. And this, Iryna, will ask you to answer this question. So noting the difficulties NASA is having with liquid hydrogen on SLS, do you think liquid hydrogen as opposed to compressed hydrogen is a viable option for powering commercial aviation, whether via fuel cells or combustion?
Very good question. So aviation is one of the areas that we are trying to decarbonize, which is as challenging or more challenging than heavy duty transportation, because of course the weight of fuel cell and the weight of fuel now becomes a big challenge. The good news about hydrogen is that it's very light. So its energy density per kilogram is 3 times higher than that of kerosene or gasoline. The challenge of hydrogen is that its volumetric density is not so high, meaning we need large tanks now to store hydrogen and redesign aircraft because of that. So, of course, liquefying hydrogen brings this volumetric energy density higher compared to compressed hydrogen. But of course, liquefaction requires a lot of challenges, technological, but somehow aerospace industry although it has challenges, it does manage to resolve some of those challenges. So the question here comes also combustion versus using fuel cells. Of course, we want to use fuel cells because there is only no NOx production, only water is a byproduct. And Jimmy says he's excited that water is the only byproduct. Aviation industry is not so excited about water being the product because of contrails. It's the droplets of waters that form and can stay in the environment and essentially trap the heat, act as greenhouse gases. So that's one thing that we can resolve by, for example, combining fuel cell and gas turbine together and passing air from fuel cell into the turbine, condensing that water onto the turbine blades and essentially eliminating that problem. But coming to question whether we will have fuel cells, for example, in aviation, I think we will do, because for short duration flight, batteries might do it, but batteries are still too heavy and there is no way battery will meet the industry standards for weight. Fuel cells can do that, but they're challenge in short flights too and low altitude flights. The higher altitude flights challenge comes from low pressure of air, because air is, you need hydrogen and air to react in fuel cell, and air at low pressure, you need a compressor. So then you use part of fuel cell power to drive a compressor, which is a challenge. So yes, I think we'll see a lot of hydrogen in aviation in coming years, and a lot of industries already investing in that, whether it's combustion, and liquefaction will certainly help. Thank you.
Great, thank you. Yeah, I think in the shorter kind of commuter flights, we're already seeing some aviation happening. So I know that there's still lots of technical challenge for sort of longer range, but we're making good progress, it seems like. Yeah, thank you, Iryna.
Sophia, I would just add that there's the big companies are looking at this. Especially Airbus. But if you look at electrification of air transportation right now, especially in countries which are leading this, like Norway and Finland, where their domestic, I believe in Norway, their domestic flights are to be zero emission by 2040, and Finland 2045. That's not that far away, and they're doing it by batteries initially for the research. But any learnings that they get from batteries will be transferable, in my opinion. Certainly, large parts of this to hydrogen, because you're electrifying transportation anyway. So this is really happening in real time right now.
Yeah, that's a great point, and also a great segue, Jimmy, into our next question, which is, how does hydrogen compare to batteries in energy storage by weight and volume? And so I think, Ahmet, this is a great question for you to start with, and then we'll open it to others to add on to.
Sure, and actually this is a good follow-up question on some of the things Jimmy and Iryna answered in terms of the gravimetric density, energy density of hydrogen, and then to increase the volumetric density, we are compressing hydrogen at high pressure or all the way to diluted. But even for compressed hydrogen, using compressed hydrogen in a fuel cell will have certain advantages compared to batteries. And before I go into detail, just to clarify maybe how hydrogen fuel cells work, hydrogen fuel cells are not that different from the batteries in the sense that they both power an electric drivetrain, if we are looking at especially on-road vehicles. And we explained that in the previous questions, it is electrochemically converting hydrogen to convert that into electricity and power the fuel cells. The difference is in fuel cell vehicles, the energy is stored in the hydrogen tanks, and then fuel cell is converting that into electricity, whereas in batteries, all the energy is stored within the battery cells, which is adding weight. So in other words, as we want more and more energy density, especially, for example, for heavy-duty trucks, we need to put more batteries, which will come at the cost of more weight. Whereas in fuel cells, we can decouple this energy and power requirement in the sense that we can use the same fuel cell to power, let's say, a heavy-duty powertrain, but like scale the hydrogen tank. So to control or design the energy density depending on the application and range. So this is where fuel cells or hydrogen-powered fuel cells will have one unique advantage, especially for higher than energy density applications and heavy-duty applications.
Excellent. Yeah, that's okay. Excellent. Okay. This next question comes to us from David Van Dyken at CPUC. The number of hydrogen fueling stations is very limited. How do we expand the network of those fueling stations? Will this influence the greater adoption of hydrogen-fueled vehicles? So, Jimmy, I know you drive a Mirai, so I think, right? Still, yeah. Maybe just a couple thoughts on this. I have thoughts on this to add as well, but please go ahead. And you're on mute.
Look, if you drive a hydrogen vehicle, having easy close access to hydrogen is very convenient, no question about it. And having more hydrogen stations would be a big plus for that. Again, no question about it. Part of the challenge is right now, there's 10,000 light-duty vehicles in California that run on hydrogen, and they're kind of concentrated in these particular areas. And as long as you stay within those areas, assuming that there is hydrogen at those stations, then you're okay. If you move out of that, you do have issues, which is one of the challenges that we're facing. So how do we expand more stations, right? This is one of the ideas which I was actually floating with a number of transit agencies. Okay, so Stanford has a collaboration with AC Transit. And one of the things that we're looking at is comparing the different kind of drivetrains for the vehicles. And one of the ideas, especially if you look at AC Transit's station in Emeryville, it has both an internal station, which goes and fuels their hydrogen buses, but they're also having an outside station, which is in the public domain. People can go drive up and people can use that. And one idea I've always had was, boy, if a number of these munis actually adopt hydrogen in their bus fleets in order to be compliant with the Innovative Clean Transit Act. Given this audience, I'm sure they know what that is. I won't need to go into that. Then also you have a number of stations all over the state. And I think there's similar kind of ideas when you start looking at additional adoption of heavy duty, which is now you have these stations which can be both used for heavy duty as well as light duty. And so that's one way to do it. Certainly there's other ways. I know that a number of people have been advocating money to build out 1,000 stations, which would be fantastic. I think you could cover the whole state with that. I just think that we also have to be open to other ideas on how we can increase the number of stations and the supply of this concurrently.
Great. Maybe I could just add a couple of comments because our office does a lot of work on infrastructure development on both sides of the technology, and on the hydrogen side, it is true. I think that infrastructure is by far the limiting factor. As we understand it, it's the demand for these vehicles that's not it's there, and the auto manufacturers want to make sure that drivers have the experience that they expect from very visible, very well-known manufacturers, right? So the state has a goal of 200 stations and has funding to get nearly there by 2026 or so. I think that one of the challenges that we're finding on both battery electric charging infrastructure and hydrogen infrastructure is the pace at which we need to be deploying this, and on the ground challenges with permitting, getting energized. And so there's some of the problems that we need to solve around ramping up the number of stations, charging stations, hydrogen stations. It is really around working with the local jurisdictions and finding ways to streamline those processes. So my personal opinion is it will influence more adoption, and that won't be the limiting factor. Won't be people wanting to drive these cars.
Gia, I don't know if the audience is fully aware. In looking at hydrogen electric vehicles versus battery electric vehicles, the charging time is very different. This is one of the appeals. So if you're looking at like you pull up to a gas station and you gas up your car, right? 5 minutes and you're on the road again, right? That is everyone's used to that. It's a status quo. That's what they're expecting. And that's one of the things that's kind of appealing about hydrogen vehicles is the same kind of fueling time. You pull up, you put in the hydrogen, and then you're on the road again in 5 minutes. one of the challenges with electric vehicles, especially, and the bigger the batteries, like we go in heavy duty, is the amount of time it would take to charge that. Okay, so if you keep the same amount of power, the length of time is going to start becoming very long. Okay, if you add fast charging and other things, you're talking about a tremendous amount of power that's got to be on standby in order to charge these vehicles, electric vehicles, battery electric vehicles, in a very short amount of time. And that is a big deal, by the way, especially when you're talking about heavy duty commercial applications or in the munis. Okay, in the if you're looking at buses and you're going to have a bus sitting there for 5 hours charging versus a bus that goes in there and boom, 10 minutes they're on the road again, it's a big deal. So the operational aspect of this is a big deal, and I'm not so sure how many people understand. One of the big drivers and appeals of hydrogen is the fast charging time.
I would like also to add from the experience of National Fuel Cell Research Center, we have been managing our hydrogen refueling station for many years already. And it's one of the older designs, so we're looking to build a new one. We have a bus charging and also a fleet of cars. There's plenty of fuel cell cars around Irvine. So one of the challenges is actually the fact that the hydrogen is currently being delivered as compressed cylinders. And so we rely on kind of gas companies to do that. And if the supply disruption happens, then we run out of hydrogen. So one solution to that would be generation on-site of hydrogen or storing hydrogen on-site. So there is currently, you can use electrolysis, you can use other methods to do so. So that's kind of where the direction of research currently and demonstration projects going to.
Thank you. All right, our next question here is from Woody Hastings with the Climate Center. How do we ensure that all hydrogen used for any application is renewables-based electrolytic? And I think maybe Ahmet or Iryna, if you want to start there. I see Jimmy smiling, so maybe whomever has who wants to jump in first.
Okay, I can jump in. Look, I think we would all like that. Let's just keep some things in mind. If you look at the amount of power, electric power that California uses, okay, and if you were to convert all of the gasoline and diesel that California uses and convert that to power, okay, so that you can generate the hydrogen electrolytically, you could just do the back of the envelope calculation. You would have to double the amount of electricity, okay, that California produces and distributes right now. That's a really big number. That's a really big undertaking. So I think we have to look at how we're going to optimize the transition at the lowest cost and the most effective way of doing it in the time period that we need. You know, we're not talking about we got hundreds of years to really address this. We're talking about decades. And if you want to say, I'm going to double what California's infrastructure is for the grid and power generation in order to convert and translate this is a big undertaking. So all options have to be on the table. We all would love, in my opinion, to generate hydrogen through electrolytic, through renewable energy. I think we would all aspire to that. But think about how much power that will require. Literally, you're going to talk about an enormous amount of generation, and it really, ultimately, you would like it to be electrolytic with renewable electricity as opposed to electricity that's, generated by fossil fuels. So I think we have to, in my opinion, keep all these options on the table and see how can we optimize cost, time, everything to enable this transition. I hope that answers your question.
Yeah,
I would like to add something, Gia, that's to that explanation. I think we should also be aware of the fact that hydrogen will have another potential as a fuel as a clean fuel for long-term, long duration energy storage. So Jimmy made some good points. So we don't really have to produce hydrogen like on demand, but we can also produce hydrogen when we have excess energy generation, and then use that to convert that electricity into hydrogen, because otherwise that energy or electricity will be curtailed, and then use that hydrogen for other applications, again, later on, or even to provide power back to the grid. So there is also this secondary, a little bit maybe overlooked role of hydrogen beyond just powering fuel cells, but as part of the power and storage infrastructure.
And I would just like to add to Ahmet's and Jimmy's comment that the reason we use hydrogen instead of batteries for storage in this scenario is that hydrogen is much better when it comes to like 10-hour window. After 10 hours, hydrogen is much better for storing and can do also seasonal. You can store energy, electricity into hydrogen in winter and retrieve it in the summer. And this is something batteries currently cannot do.
So, Gia, that's a big deal, by the way, right? Because as we ramp up in California to have greater amounts of renewable energy, right? SB 100 and so on, you're going to create larger and larger. I don't know if the audience is familiar with the duck curve. Okay, that's the amount of net energy that would drawn from the grid. So during the daytime, when we have all this solar and the solar is increasing, okay, we're fine. In fact, we're going to over-generate. We're going to generate more electricity than we need. Okay. Now, when the sun sets, you're going to have to get the energy from somewhere else. This creates a famous, duck curve where we have this enormous ramp of power. So if we embark on this journey, we're going to put in more and more renewables, and they're intermittent. Okay, which they are. Okay, you have to store it, and if you're going to store it for short durations, batteries work pretty well. For long durations, it's a real problem. And if we get to 80–90% of renewables and they're intermittent, you're going to have to store a huge amount of energy. And right now, we already curtail a fair amount of energy. I think CAISO, there was a presentation on CAISO at Stanford where there was already some periods where we were curtailing like 5 gigawatts, 5 gigawatts of energy, just as a benchmark to that, right? California uses about 30 gigawatts. So, and that's with our current amount of renewables with solar. If that increases, it's going to go higher. So that journey is going to continue. That trend is going to become bigger. So I think the question is, how can we not curtail renewable electricity, and how can we use it in other applications? And long duration storage is one area we need that right now. Actually, we don't have a real good solution to long duration storage.
I think just one more point that I'd like to add is, as we think about renewable hydrogen, I think it's important to not only think about electrolysis, right? There are other ways to produce hydrogen from renewable sources that in some cases can have negative carbon intensity, right? So as we think about different feedstocks and biomass and other kinds of things, there are many ways to produce hydrogen renewably. And so as we think about renewable hydrogen, let's not get stuck in just thinking about electrolysis. Yeah, great. All right, let's move on. Our next question is from Mix Skavarla, and he's from the California Hydrogen Coalition. And the question is, how can renewable hydrogen production from biogas and biomass help mitigate wildfire risks? Good, this is a good segue, I guess. Agriculture and municipal waste biomass related emissions, as well as methane from landfills and wastewater treatment. ARB's scoping plan indicates hydrogen production from these waste streams is necessary to help us achieve carbon neutrality. So kind of on the point of that last comment, anybody have more to say there? I mean, I guess I could just say a few things, Nick, about this, which is kind of adding on to what I said before. There are many ways to do this. And I think that at least in California, as we're thinking about some of the organization, the state's getting around the hydrogen hubs effort and getting organized to think about how do we create a renewable hydrogen economy here in California and a real thriving market, thinking about the different assets we have within the state. In the far north, we have a lot of woody biomass, right, that we need to deal with that's already burned, and those things, and a lot of forest management that needs to happen. And so thinking about where we can have renewable production utilizing the resources that we have in different parts of the state, I think will be key to achieving some of our goals and having as much in-state production as we can for the volume of hydrogen that we anticipate needing to achieve our goals that are in the scoping plan. So yeah, and then there's many other ways to produce hydrogen. In California, the Energy Commission has been giving some grants to different forms of renewable production. There are some different demonstration projects happening around the state, which we can talk with anybody about offline. But looking at different ways from wastewater, from dairy methane, from landfill gases, and there are many ways that we can demonstrate this. And so I think continuing to invest in that and see how we can push these technologies and what's scalable, what will help drive down costs is all important.
Yeah, I would like to echo what you said. Oh, I'm sorry. Go ahead, Ahmet.
Go ahead.
I was just going to echo what you said, Gia, which is like, in some of these waste streams, they produce methane. And if you're able to then use this methane to produce hydrogen and then capture the resulting CO2, that's another avenue to create low carbon hydrogen. So I think we have to consider these other options and find ways to produce low carbon hydrogen. I think electrolytic is very attractive, and people would like to just gravitate toward that, but we really have to have all options on the table, in my opinion, to allow us to generate the amount of hydrogen that we will need. Ahmet?
Thank you. I just wanted to add something from the California Going to Net Neutrality report that came up, I think, 2 years ago, where they look at several scenarios, as Gia also explained. And then one of the interesting findings in those reports, which are more specific to California, is like of all the scenarios leading to like different products from biomass to different products, production of hydrogen along with electricity, of course, were among the best scenarios in terms of the highest negative emission potential. Of course, some of that includes maybe back to like power grid, or some of them in the case of hydrogen is actually to generate fuel. So that intersection, or maybe the synergy between biomass and hydrogen, I think is going to be important and a potential that can be utilized very well in California.
Yeah.
Thank you. Thanks for the question. Okay, our next question comes from Bailey Avery with Lucas Public Affairs. Question is, are any major companies or stations planning on joining this movement and adding hydrogen fueling stations? Anybody have a?
You mean in addition to the existing companies that are working in that space?
Yeah, maybe we start with who's working in the space, right? Because there are major gas companies working in the space already. But yeah, so maybe just to add on to that point, right now in California on the light duty side and moving more and more into the heavy duty side of fueling, Shell is a major player. Chevron is coming into the mix. We have First Element Fuel, which is solely dedicated to hydrogen fueling. They've never, that's their retail business. That's entirely what they do, and doing now heavy duty stations as well. Iwatani is another major station developer here in California, and they have they're a major energy player in Japan, and then of course the America's version, they're focusing really on hydrogen production and infrastructure installation. We know that there's interest from others. BP is interested in what's happening, and then globally, I think I would venture to say that most of the major oil and gas companies have some investments in hydrogen. But in California, we already have a pretty good field going and more entering. Mm-hmm. Yeah. Okay, anybody else? sorry to take that one from the panel. But,
no, I think your point is exactly right. There's a lot of, we're fortunate in California to have a very active industrial ecosystem that's already in place. And I know we're focused on road transportation, or a lot of discussions have been on road, and then we talked a little bit about planes. But it's important to realize that California has 2 of the top 5 ports in the US, and the same mandates that go about decarbonization and zero emission stuff apply to the ports. And those ports are also actively engaged right now in how to decarbonize. And so it's a very active space right now across all of transportation. And in the Port of LA, Port of Long Beach right now, there's a tremendous amount of effort on looking at how to decarbonize, port operations, and even looking at potentially ships. So.
Great point. Okay. Our next question here is, how does hydrogen compare to batteries in potential geopolitical advantages or disadvantages, for example, regarding critical or rare materials? Iryna, is that something?
Yeah, I can comment on that.
Yeah.
Can you hear me well?
Yes, we can. Thank you.
Is my connection still okay? Okay, wonderful. So when it comes to batteries, the critical materials that are there is cobalt and nickel, and many companies looking for so-called cobalt-free batteries or iron LFP type of cathode materials to avoid that cobalt, which is currently mostly mined in the Democratic Republic of Congo, and all of it goes pretty much through China. So there is this supply chain that can be easily disrupted. So for fuel cells and electrolyzers, the critical materials are platinum and iridium. And so, of course, they're also precious metals and expensive and being mined currently also in Africa. And owned by major European companies such as Johnson Matthey and Umicore and others. So the question also, I would imagine that, of course, we're striving to use as much platinum in fuel cell vehicles as we do typically in internal combustion engines. They use platinum for catalytic conversion. So if we reach the target, it's kind of, it will be comparable already. There is existing market in catalytic conversion using platinum. Another point is recyclability. So battery industry is already looking into recycling batteries, recycling those materials, but it's challenging and it's really energy intensive process for batteries because they use organic electrolytes. Essentially, you cannot open up battery in kind of environment that can fire hazards and all of that. So you really need to have very well controlled environment, and this leaching in this heavy acids is also environmentally unfriendly process. I believe for fuel cells and electrolyzers, the recycling process will be much more smoother. You can work in ambient environments. You can open the cell. You can separate platinum and iridium from the used stacks. So this yet to be proven. There is not yet recycling industry for fuel cells, but companies like Plug Power, who has full control of their stacks, for example, is looking into this matter.
One point that I also wanted to add, Ahmet kind of brought this up earlier, but when it comes to batteries, a lot of those materials kind of scale directly with the amount of energy stored in a battery. So as you have more batteries, you need more lithium or cobalt or nickel or what have you. When it comes to hydrogen fuel cells, those platinum group metals are only in the fuel cell itself. The hydrogen storage is done in metal or carbon fiber tanks. And so, if the fuel cells, larger, higher power fuel cells might need more of those materials, but the hydrogen storage itself, it can kind of continue to scale up and up. More storage capacity can be added without needing to resort to more and more expensive and harder to obtain metals. I will also note the Department of Energy is currently funding quite a bit of work in the area of both electrolysis and other production pathways, as well as the fuel cell, the use case for hydrogen to try to move away from and develop other technologies that don't use these same type of platinum group metals as well. So there's certainly research ongoing in that area.
Excellent, thank you. Okay. Our next question here comes from Natalie Sitzman. She's a CCST Science Fellow with the Assembly Utilities and Energy Committee. What scale of on-site generation would be needed to supply, for example, a municipal bus depot fueling station? Ahmet, is that something that you, or Jimmy?
I would recommend that you talk to Sunline. Okay, that's exactly what Sunline is doing right now. Sunline is the large muni in I'm sorry.
Palm Desert, right?
Palm Desert. Thank you. Yes, Palm Desert. And they're they're embarking exactly that, projects where they're going, because they have, they have all this open land in Palm Desert, and they can in fact put in solar and then use the electricity to generate their own hydrogen, which is part of their vision. And so, they probably have the latest numbers, which are which they've outputted, which is great because those are real numbers that they've done analysis that they plan to use in their submissions. So those numbers are probably the most accurate that, in a commercial sense, right, that you can get access to and understand. And also, I think they would love to hear ideas that other people have on that, on what their plans are.
Yeah, that's a great point. They have and
thank you. Someone popped up there. Yes.
Yeah, and
maybe
I'll put this link. I think that just, I'm not sure if everyone can see that. So let me transfer. So there's a link here to just exactly what Jim was talking about. They've been doing some really creative things there. They've been working with fuel cells in their fuel cell buses in their fleet for a number of years, as well as AC Transit in the Bay Area. And have come up, both of them have some really phenomenal studies about side-to-side comparison. Like AC Transit has the 5x5. They took 5 battery electric buses, 5 hydrogen fuel cell buses, and they looked at kind of what their needs were, what their route needs were, and what the sort of advantages and disadvantages of each were. And so, yeah, there's a lot of information out there. AC Transit also has they have on-site production in their Emeryville facility. So they are also doing on-site production of hydrogen there as well. Okay, our next question here is, do we have to choose to support either light duty or heavy duty decarbonization with hydrogen? Are there synergies between the two markets? Great question.
I'll take
yes,
that.
And go ahead, Jimmy. The answer is yes.
No. I hear that question a lot, and I always think, certainly breaking the transportation sector into light and heavy duty is one way of slicing and dicing it. But I think we have to be sensitive to the use cases. So even if you take a look, so to answer the question, is there synergies? Absolutely. And they tie into use cases quite a bit. So even if you take a look at light duty, okay, and you have a fleet operation, okay, where you have, hundreds or, maybe even thousands of these vehicles, and you're looking at having them out of a central field operation or something. All right, well, now you're going to be putting in a scenario, if you were just all battery electric, where you're going to have to build a little power station to power all these vehicles that you're going to be charging. Okay, and so the difference between charging your electric vehicle at home versus a fleet operation is a completely different use case, and the economics on that change dramatically. So I don't think you can look at just heavy duty or light duty. You also have to look very carefully at your use cases. And so there's absolutely synergy across there, depending on your use case and depending on whether it's residential, commercial, or other things. I think that looking at it that way will give you another perspective that you should map onto sort of the way you think about this. And anyway, I'll stop there.
I could maybe continue briefly. I think that was a good explanation of or the use cases are important. And I would also agree that there will be synergies. And I think there is this common thought that hydrogen is going to be more suitable or will be a better option for heavy duty vehicles, which is true, but it doesn't mean that there will not be an opportunities for light medium duty. It is not just about the weight class, but also the utilization or fleet characteristics. So there could be, for example, a medium or light duty truck or vehicle that operates continuously with shift drivers with really narrow downtime for charging. And in that case, actually, for that continuous operation, light duty vehicles will be powered by hydrogen. And also another example is currently there are electric forklifts powered by hydrogen operating 24 hours a day, which are considered really lighter duty, vehicles in warehouses, but they still operate on hydrogen. So it will be a function of duty cycles, route flexibility, whether there is downtime for charging or the operation includes going back to the base for charging, etc. So there are, I think, other cases of maybe medium duty or even lighter duty vehicles where hydrogen will be beneficial.
I would just like to add that, so for Class 8 trucks, Kenworth did analysis showing that payload, if you use batteries, payload will be reduced by 1/3. If you use hydrogen, you're not going to have any payload reduction. That's why hydrogen is so promising for heavy duty transportation. For light duty transportation, battery electric vehicles are on the roads. There are millions of them, and they're getting to be cheaper and cheaper because of battery costs dramatically are dropping. So I think it's of course we'll see some light duty fuel cell vehicles in California, but I think it's still going to be dominated by battery electric vehicles, considering 2035 timeline that we have to stop selling internal combustion engines in California.
Just chiming in, I think people would find the 5x5 studies that AC Transit is publishing very interesting from that standpoint. Because they're looking at exactly that kind of question, which is, what vehicles or what propulsion system is best suited for what kind of length and other things. And they're looking at it within the Muni application, but the learnings associated with that are really, you're going to put the link? There you go. Was that you, Gia? Thank you, or Juan. Thank you very much for putting the link on that. So these kind of learnings are happening right now. And to map the learnings associated with each of these applications and make them more widely available for people will be very important, because we're learning about the cars, we're learning about the buses and stuff right now, but the trucks are right behind them. And we need to understand the economics and other infrastructure needs and everything as we transition to zero emission, and look at the trade-offs associated with one kind of propulsion versus another. And they really do have areas of overlap, but they also have unique characteristics that make it more suitable for one versus the other.
Brian, yeah,
and then and then finally, just to sort of re-highlight kind of that synergies between light, medium, and heavy duty applications. I mean, as some of those delivery fleets, municipal fleets, some of these more medium and heavy duty applications, they can really form those sort of refueling hubs where much like the current example of a bus fleet also providing public light duty vehicle refueling, the same can be done for heavy and medium duty truck fleets, where an influx of one kind of vehicle can provide the infrastructure support and even some of the other supporting infrastructure, like trained maintenance staff and personnel and some of these other aspects that are needed and aren't strictly related to the refueling station, would certainly transition well between those, both the light and heavy duty applications. So yeah, absolutely, there's quite a few synergies there as well.
And I'd like to just add one more thing that I think we haven't touched on here, which is what, as we understand it from when we hear from the auto manufacturers or from those that are developing components and thinking about how we scale the hydrogen market, what we've been told is that the light duty and heavy duty markets actually are synergistic and they must work together. Because as we start to think about some of the biggest challenges we have, like we often do in an early market, cost is a big one. If we want to see big reductions like we have in batteries, in solar, in wind, right? It's scale that drives that, right? And so as we think about scale on the component side, it's the light duty sector that drives that component scale. And on the heavy duty side, it drives the molecule scale, right? So together, it creates a system where we help drive down costs and we help drive up scale. And so it's actually very important to have both. Okay, so we are getting really low on time. This is our last question, and it's going to be our speed round. So 30 seconds or less. If you could make one change today to help support the growth of the hydrogen-powered transportation in California, what would it be? Or it's a choose your adventure, or you can say what you're most excited about when it comes to decarbonizing with hydrogen. So we'll just go around. I'll start here with Brian.
Yeah, so one of the things that I'm most excited about, and I think does directly apply to increasing the penetration of hydrogen, is just a wide variety of ways that hydrogen can be produced by electrolysis, thermochemical pathways, steam methane reforming, biogas, but also the wide variety of uses for hydrogen, backup power for data centers or other critical electrical infrastructure, long-term energy storage, all sorts of different applications, vehicles, rail, maritime, all of these different applications can all benefit from decarbonization through hydrogen, and I think that's a really cool way that hydrogen can do a lot of good, and they can all benefit each other.
Thanks, Brian. Okay, Jimmy, let's hear from you.
So what's really exciting to me, and I'm going to go beyond just hydrogen, is the rate of innovation right now in R&D on sustainability. And hydrogen is one subset of that. Batteries is another, where right now, if you take a look at how fast things are being developed and scaled right now, it's really exciting. I mean, it used to be, I think, where the rate of energy innovation right now is just amazing. It's just, it's like, what was true 1 month, and then the next month is like, wow, now they can do this, or they're able to scale it's that big or whatever. That rate of innovation, and it's going to accelerate, is very exciting. So now it's going to be necessary for where we want to go, and to see that happening, gives me hope that, wow, we're going to actually do the global energy transformation the next 2 or 3 decades. There's a real optimism about doing that. It's a big undertaking, right? Changing the global energy from where we are now to where we need to go. Even if you add everything together right now, we're just beginning that journey, and we have, depending on who you talk to, right, we only have a few decades, so we gotta do a lot of things very quickly and scale it. Anyway, that's what excites me.
Thank you, Ahmet.
Well, I will say the unique role of hydrogen from its potential, like to be produced from a diverse range of feedstocks, then its ability to be used as a long duration energy storage, like molecule, like as a clean molecule, and then to be delivered for many end users, including transportation. I think that whole circularity, I think, makes hydrogen unique. After all, it is not an energy source, as we know, and I think it's its potential, the fact that it can be an energy carrier and it can be used as a like convertible energy molecule between all these applications, all the way to different transportation applications. I think makes it really a great solution to help decarbonize all the sectors.
Iryna.
I'm a professor, so I'm an academic, and our mission is to educate students. So what I'm really excited about this new generation of students being excited about sustainability and environment, and wanting to enter the field to kind of produce more sustainable either fuels or decarbonize our environment or care about clean air. And essentially what's exciting about here in University of California, Irvine, we have this demonstration project. We have the refueling stations, we have the cars, we have the bus, so we can point to students and say, hey, this bus drives on hydrogen. This is how you can refuel the car. So we have a lot of use cases here in the university, and students get so excited, and it's just incredible for me to be there to educate them and to see how far they can go. Thank you.
Wonderful. Thank you. Okay, I really appreciate it. I'm going to turn it back to Sarah. Thanks for giving us a couple of extra minutes here. It was too hard to tear ourselves away.
I completely understand. Thank you, Gia. Thank you to all of our panelists today for sharing your time and expertise. And of course, thank you to our audience who joined us. If you'd like to watch this briefing again, it was very good, or have a colleague who was interested but couldn't make it, it will be posted on our website, along with the one-pager and contact information of the experts you heard from today. I hope you all have a good day, and I hope everyone is able to stay cool. Thank you.
Thank you, Sarah.